In section 7.5, we're going to describe the energetics of covalent and ionic bond formation and breakage. We're going to learn about the Born-Haber cycle, and then we're going to use average covalent bond energies to estimate enthalpies of reactions. So the strength of a covalent bond is measured by the energy required to break them, separating the atoms participating in the bond. Bond energy or bond dissociation energy is the energy required to break a covalent bond in a molecule in the gas phase. When a single bond is broken, the bond energy is the same as the standard enthalpy change of the reaction. So we saw this before. We see now that if we have X bound to Y, we break that bond, we're going to get a bond energy that is going to be equal to the change in enthalpy, standard change of enthalpy for that reaction. So each bond type has its own associated bond energy. Shorter bonds have greater bond energies. Longer bonds have lower bond energies. Double bonds are stronger than single bonds. Triple bonds stronger than double bonds. Adding multiple bonds therefore decreases the bond length and brings the nuclei of the bonding atoms closer together. Here we have a table of some common bond energies and bond lengths, and we can see that the shorter bond lengths lead to higher energies, whereas longer bond lengths have lower energies. So we learned about the standard enthalpy in chapter 5. There we were using standard enthalpies of different reactions in order to calculate the standard enthalpy for a specific reaction. We can do this exact same thing with bond energies. And it has a very similar form where we're going to add up all the bond energies of the bonds broken. Those are positive values. And we're going to subtract out all of the bonds formed. Here are the bond energies for various different bonds. This is a table that you're going to see in your book, table 7.2, and you're going to need this guy for the homework, so you should go check that one out in the text. Let's consider the following reaction. We have methane, and we're going to break that down into a carbon atom and 4 hydrogen atoms. We're putting energy in to break those bonds. We see that our delta H, or standard enthalpy, is positive. Since bonds are only broken, the standard enthalpy is positive. The overall enthalpy change is 4 times that of a CH bond. We can consider the formation of hydrochloric acid. Here we've broken an HH bond and a ClCl bond, and we formed two HCl bonds. Our bonds broken are going to be for the energies of the DH and the ClCl bond. We're going to subtract out from that the energy in that HCl bond. Notice that we didn't change the sign of any of the bond energies. We just inputted into the formula and we multiplied it by how many there were, and we wind up with a negative value of negative 185 kilojoules. So we could expect this to be a spontaneous reaction, to happen all by itself and release energy. Ionic bonding. So we know that ionic solids are made out of different ions that are held together in a lattice. So the energy that's holding that lattice together is called the lattice energy. Note that separating the ions requires energy, an endothermic process. Therefore, lattice energy values will be positive. So we're going to expect positive values for this. So we have an equation for calculating the lattice enthalpy. However, it's really pretty hard to make this calculation for any given lattice. Determining what this C constant is for your specific lattice is pretty tricky. But just by looking at the form of this, we can make some generalizations. Ions with higher charges, meaning that this Z plus value or Z minus value are higher, are going to have higher lattice energies. So are atoms with lower atomic radii, meaning that this R naught value down here is going to be smaller, making the whole ratio larger. The Born-Haber cycle is a special application of Hess's law that offers an alternative method for calculating lattice energies. The lattice energies can be calculated from other known enthalpy values. So what you need to know is the enthalpy of formation of the compound, the ionization energy of the metal, the electron affinity of the nonmetal, the enthalpy of sublimation of the metal, and the bond dissociation energy of the nonmetal. If you knew all of those things, then you can put it into this equation here and calculate the lattice energy. Keep in mind that lattice energy cannot be measured directly like bond energy. We have to do several different measurements, or we have to rely on calculating it using the first equation. But we can get at it using this value here. And here is the overall diagram. So what we want to get is to this piece right here. So if we're able to add up all of these values and then subtract out this value here, we can get this missing piece here, which is the lattice energy.